Alright troops, Yoker Uni presents Physics! It's me, Valdo here, to give you your first lecture in physics for Yoker Uni. Semiconductors are pure heavy boring, man. When your physics teacher in school pure hits out with these crap drawings on the board talking about atoms and electrons. Well, I'm here to tell you that semiconductors are actual heavy boring anyway, but you need to know about them for your physics exam. Nail it, big chap. Semiconductors are everywhere around us, man. You can't no see them. Inside computers, you've got chips with semiconductor processors. You've got LEDs which are pure everywhere now because they're heavy good with energy saving crap. Traffic lights I've got on them. Wee Baz has them for his Audi R8 headlights, but I'm going to heavy tan them with a screwdriver for my motor. This saddle here spent pure ages making a cube for LEDs. What a button. If you head down to Bears Den, you'll find solar panels on the roofs for collecting sunshine energy. You're in Glasgow, mate. Unless your solar panels collect rain energy, then you're wasting your cash. Go to a desert. This is an LDR, which stands for light, robots, nothing that. To make semiconductors, you pure have to dress up like a white ninja, because they're heavy made in clean labs. If you sneeze a bogey in one, then it's pure wasted. Right, let's take a swatch at how you actually make them then. Cue the tape smudge.
Beanie bother, Valdo.
For these next couple of diagrams, the big black balls are the nucleus of an atom, and the wee red balls are the electron. In a conductor like a copper wire or a bit of metal, your electrons are free to move. What actually happens is they pure fire about as if they're MWI. Look here, they're going everywhere pure mental. If you give these electrons a potential difference or a voltage, then they pure heavy boost towards the positive plate or the positive terminal. Which means, boys and girls, you have a movement of charge, which we know to be a current. Let's have a look at the periodic table. See if you ask any chemist about the table, they'll pure pretend to know whatever it is, but they've not got a clue. Hafnium, tantalum, niobium, yttrium, calcium, what's all that rubbish? In the periodic table you've got all these mad things on the right hand side. The group A elements are the noble gases. Pure heavy chilling out because they've got all their electrons in their outer shells. What you need is 8. They've got 8. They're just kicking back watching Jeremy Kyle in the mornings. No having a worry or a care. Jammy buggers. These ones here are in group 4. They're the ones you've got to watch. We're going to have a look at silicon. Group 4 elements have only got 4 electrons. They don't like that one bit. They're going to go pure rage trying to get electrons for anywhere and everywhere. Jakies. Silicon are sneaky. They form silicon crystals which are closely packed atoms together, forming nice rows and columns. If you notice here, each atom has access to 8 electrons because they have a wee bit of a contract, they share it out with each other. Heavy clever, by the way. If an electron was to ever disappear from an atom, it leave a hole behind. And then you've got some problems, because it's like, oh, you, geez one of your electrons. And the other one's like, no. Alright, here you go then. But then he's like, oh, you, geez one of your electrons. And he's like, alright, take it. But then he's like to somebody else, oh, geez one of your electrons. And then you got a whole big problem. But eventually some smart buttons somewhere realise they can use this to their advantage. Enter the semiconductor. The secret is when you make a semiconductor you need to grow it with a thing called impurities. This is also called doping. I know, it sounds weird, but it is. Elements in group 3 in the periodic table, like indium, only have 3 outer electrons. This is introduced as an impurity when you grow a positive type or a p-type semiconductor. Instead of having 8 outer electrons, indium only has 7, leaving a hole. And then you have the problem again. Oh, gives an electron. One silicon atom gives up an electron, and then there's a hole left there. And then that asks for an electron. from somewhere else, so you have a movement of electrons, or a movement of the whole. When your impurity is a group 5 element like arsenic, then when you introduce that as an impurity, you've got 9 electrons available to the arsenic. That's no good, it's got 1 spare. So that electron's like, where am I going to go? So he just fires about. So he's just going around the other atoms. They're like, no, I can't come in, no, beat it, get to, no, go away, beat it. Ergo, you have a movement of an electron, which is a current. And this is a negative or N-type semiconductor. Right, these P-type and N-types are pretty useless on their own, so let's have a swatch at some videos. This one here is called the diode or the junction diode. A P-type and N-type brought together. As you can see, sometimes a hole and electron drift across the border between them. Eventually you build up a static charge on one side and the other, and then no further electrons can drift across because they're repelled by the static charge on the P-type. Dead easy, isn't it? Here we've got a junction with P-type and N-type and a depletion layer. But now we've got a battery or a cell. When we turn the circuit on, the electrons heavy go towards the positive plate or terminal, and the holes, because they're positive charges, go the other way towards the negative. If I reverse the battery, then you know what's going to happen. The holes and electrons are going to go the opposite way, and that makes the depletion layer bigger. Making the battery bigger makes the depletion layer bigger. Here we got a battery circuit, we got a junction again. As before, the electrons and holes recombine in the middle, and when they do that, they form a photon, which, as we all know, is light. So this is how a wee LED is made. A solar panel is when a photon of light hits the depletion layer and forms a hole and an electron. And because of the depletion layer, they heavy boost towards one side and other side. Well, we can use this to our advantage. Because you're getting extra holes and electrons, we can make that into a current. And when we can store that charge in a wee store thing, let's pure turning round in the bottom there. A solar panel takes in light energy, makes an electron and hole pair, and then you store a charge. This is called photovoltaic mode. Sometimes you get a situation where you've got a minority charge in each of the P-type and N-type semiconductor bits. And these wee minority charges drift across the depletion layer, because the electrons go towards the positive, the holes to the negative. This is called a leakage current. When a photon comes into the depletion layer like a solar panel, that forms even more electrons and holes. And because of the electric field in the depletion layer, these wee things fire off to the side. This makes your leakage current a wee bit bigger. Making the battery bigger doesn't do much. So in other words, when I shine light onto this thing, the current gets a wee bit bigger. Remember, boys and girls, back to standard grade. Light goes up, resistance goes down, which means your current goes up. That is an LDR. The lecture, let's have a look at an application of semiconductors. Let's have a look at the MOSFET. MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. It makes use of the fact that in your P-type semiconductor, you've got a minority electron charge. Obviously you're no stupid, so you can follow the circuits. Remember, electrons go to the positive, the holes go to the negative. Don't know what this Jakey's doing with the arrow, by the way. That would be smudge. Right, here we go. We turn on the gate, so you can see the holes go to the bottom because it's negative, and the electrons go to the top because it's positive. Then you've got a wee layer of electrons between the two negative bits at the source and the drain. Make the gate voltage bigger, you get a bigger channel. When you turn on this voltage, then you got a current moving between the source and the drain because it goes from negative to positive. Turn off the gate, nothing happens because you don't have your wee N channel. Is it that simple? Aye. Just like any transistor then, it conducts only when it's got a certain voltage at the gate. Ergo, it's an electronic switch. Right, that's my lecture over on semiconductors. Catchy Versace.